Hi everyone, first of all I would like to thank the third international webinar on geology and earth science organizing committee, and especially to Robert Martin for the invitation to talk about this topic. So we're gonna talk about multiple thermochronometers applied to the quantitative analysis of compressive systems, the southern sub-andean fall and thrust belt of Bolivia from source rock to trap. The evolution of fall and thrust belts, extension system, etc. require chronological data constraints in order to determine the rates related to the interaction of surface and subsurface processes and quantifying the time involved within the components of the petroleum system, reservoir, seal, source rock, and trap timing. This is an important phrase I wanted to share with all the audience. There are some key points to be clarified or to study or to go with, deep into in order to understand the study area. The first of them is the magnitude of pre-Cenozoic tectonics and its influence in oil and gas systems. The second one is the timing of Andean structural growth and chronology of the formation within the fault-related anticlines. Those are the trap structures or the conventional reservoir targets. The third topic is the oil and gas thermal parameters definition. Here we present a possible solution that is summarized in Hernandez et al. 2021, included in the special issue about thermochronology of South America of the Journal of South American Health Science. Some powerful tools here we present are related to thermochronological analysis, mainly related to apatite fission track and uranium, thorium, helium data, and how we integrate these thermochronometers with the geological constraints in order to develop time temperature numerical modeling. The second step is the absolute rate related to uranium red shrimp in order to determine the crystallization age or depositional age. And the third data we integrated is the paleo-magnetic data. And we talk about, when we talk about thermochronometers or low temperature thermochronology, what we wanted to study is the time where a particular rock volume was heated up to a certain temperature, or when it was cooled down under a certain temperature related to our geological evolution. So in this way we have these four balloons related to helium, uranium, thorium, helium in apatite with this closure temperature and time involved, the apatite fission track related to this data, and the zircon systems. What we want to do is to integrate these thermochronometers and the geological constraints in order to develop numerical modeling to establish some TT paths, time temperature paths related to the geological evolution. So in relationship with numerical modeling, what we want to get is to adjusted and statistically reliable time temperature trajectories. How do we do this? We do some forward or inverse modeling. In the first case, we establish some time temperature trajectory while we observe the matching within a thermal history we design with the measured data. In this case, we have this thermal time temperature evolution. That is, we have some cooling down phenomena and some heating up phenomena and cooling down again, and we see how the measured data, in this case the confined track length distribution related to apatite, adjust this particular model or not. In the second case is inverse modeling, where the geological constraints are really important things. We want to integrate our geological knowledge coming from surface or subsurface with the thermochronological data in order to establish this time and temperature evolution. And we want to see how the measured data, in this case the apatite fission track or the helium in apatite, is combined with our geological constraints. Those are these boxes drawn here, and how we get a statistically reliable thermal history for our working area. validated through different statistical parameters. So this is our working area in the southern part of Bolivia. This is the black square here. This is a zoom in. We have all these yellow fall related anticlines. We're gonna have a quick look about this white rectangle that is zoom in here. These are our fault related anticlines in blue and our synclines in green. And these are the sample distribution we analyze through these different thermochronometers. The outcropping areas go from the Devonian to the Miocene, and this is the distribution of the samples we analyze. The tuffs levels dated through uranium lead are the yellow spots, the sample TT model are the red ones, and the oil and gas thermal history model is located here. We're going to talk a little bit in detail further. So in order to answer the first key point to be clarified, we are going to talk a little bit about magnitude of pre-Cenozoic tectonics. So in the study area we have this Ordovician to Miocene stratigraphic columns that is divided according to the main detachment levels located in the Ordovician to Silurian fine-grained sediments and the middle Devonian fine-grained sediments. These are the two main detachment levels that are modeled by trace shear in this case, representing an inhomogeneous deformation interval, and the other two, the rheological level 2 and 4, are strongly heterogeneous intervals modeled by parallel folding or simple shear. What we did here was to analyze the thickness variation and distribution related to these stratigraphic intervals that are separated by main first order unconformities from the lower Silurian, lower Devonian up to the Miocene. What we did was to pile up all the isopack maps, develop some 3D grids and put one on top of the other. And when we do this, we got this Ordovician top or Silurian base level to the youngest undeformed timeline. We get this type of surface represented that the detachment level is not flat and constant west, well, gently dipping. It is a really irregular surface that we have to take into account when we perform 3D modeling. In relationship to the second topic, we developed this balanced cross section in the area, these four related anticlines and the synclines between them, and these are the samples we analyzed. They are projected onto the section with all the thermochronometers we are going to see. What we wanted to answer was were these four topics: timing and rate of structural growth, chronological relationships, shortening transfer between structures, and control influence of pre-existing structures. According to the second, in relationship to the second topic, we wanted to see in sequence, out of sequence, simultaneous growth or diachronism timing along the structures. These are the results, the data set related to the uranium lead shrimp that is giving our tuff layers crystallization age. These are these yellow spots. These are the ages, Miocene, upper Miocene data. These are the apatite fission track. We have analyzed 11 samples. These are summarized here. Some of them are white and some of them are red because some of them were modeled. These are the age distribution. What we can see is that we have partial resets for the rocks analyzed from these Devonian and Carboniferous stratigraphic units. That is, that the closure temperature was not reached for enough time in order to completely reset these thermochronometers. And on the third data set, these are the apatite uranium, thorium, helium data for 36 samples within the study area, and getting some really important and interesting data related to cooling ages that those are going to give us some information about the growing chronology and growth rate of the structures where the samples were taken from. As we can see, there are also some older edges that were partially reset for this thermochronometer. The numerical modeling we developed for the samples. These red spots here are represented here. All these are the time temperatures models with the goodness of the good fit envelopes in this purple and the acceptable fit envelope in green. But what we can see is the heating up and cooling down phenomena that we got integrated the geochronological data and the geological constraints. Taking this as an input data, we took this heating and cooling segment divided by a fixed geothermal gradient of 30 degrees per kilometer in order to get these subsidence in red or exhumation rates for different time intervals for the different samples in the area. Here we got from old to young samples and from west to east, the same here. As we can see, there are a lot of things in common between the sample. We're going to take, for example, one of them. We can see that after the deposition age, we have these samples experience a heating up subsidence, then an intermediate cooling down, then a heating up, again cooling down, and then we're going to take a look about the Miocene history that is related to the formation of our conventional traps. This is the first time this type of analysis is related here. The rates here, the subsidence and exhumation rates are in millimeters per year. Is the same as meter per million year, but this was an interesting thing to do, combining all the knowledge we have on the area. When we go to the young history of the young interval of this, we develop chronokinematic evolution from 8 million years up to nowadays minor than 2.5 million years, and we can see how the structures are grow in order, first in relationship to the deep structures, and then when we go to younger ages, this out of sequence movement are taking place. And for example, this structure in particular is formed afterwards together with this structure to the east. That is, the deeper structures are formed first, then the out of sequence thrusting, and then this particular structure and this one are formed afterwards. What we see here is just a movie of this time evolution. As a final step, what we did in Arduino 3D software was to develop a thermal and structural modeling. This is a four-step workflow where we can combine our thermochronological data and to perform a finite element thermal modeling in order to compare the thermochronological data and the structural data we have on the area. So these four steps are the definition of thermochronological computing grid. This is a hypothetical case, but we're going to see some practical case afterwards. So the first step is to define the thermochronological grid. It can be visualized, checked, and modified in real time. We have these input sections based on our thermochronological data, and then we interpolate all these sections per 0.5 million years or 0.1 million years, and we can see here these black segments are the velocity vector for this particular time step. On the third step is the feeling of thermal properties, thermal conductivity, heat capacity, density, and velocity for all grid sets. All the temperature, all the combination of variables can be set here: basal temperature, basal heat flow, surface temperature, atmospheric cooling rate, lateral or time varying. So we can set up a combination of parameters, and then we are going to compute the thermal state at each time in the reconstructions. We can we can plot our samples measured here, but we can also design some hypothetical samples in order to see how the time temperature evolution is, and we can also see the isotherms related to that. When this is applied to the Bolivian structure, this structure in particular, we divided our column involving the deformation in this interval with these rock types and thermal properties together with density. We set some boundary conditions related to basal temperatures, different values were tested, surface temperature and atmospheric cooling rate. What we got is this structural evolution from 7 to 0 million years, where, as I already commented, an onset of the deep structures related to this tri-shear model structure, and then beginning of breakthrough out of sequence thrusting related to the back limb of the structures, and then the beginning of main uplift of the structure. 70 sections were interpolated in relationship to these time steps. When we see the thermal evolution, here is the location of the samples, 1 Devonian and 2 Carboniferous samples, and we see the movement of the samples we are analyzing and how they are plotted in this time temperature scenario. To the right, we see the layer velocity vectors for all the evolution and the grid velocity vector when these stratigraphical intervals are divided into cells for the finite element modeling. So in this case, we did this is a comparison of the time temperature evolution of this blue, green, black, and time temperature paths got from the finite element thermal modeling, and how this is compared to this gray area that is the inverse modeling coming from the other software, that is Helium FT. And we see that the best fit is related to the 200 degrees basal temperature. Here is where the 3 samples are plotted. So when we got to the 200, we tested different geothermal gradients or basal temperature, and the 200 is where the model edges and the model edges and the measure edges are in concordance. To end the presentation, we combine all these thermochronometers and geological constraints to develop a thermal history model. We did it in a 1D Petromod 1D in relation to this green spot, and we evaluated the 3 main source rock in the area: the Emsian Eifelian Gibbetian interval, the Lockwoodian interval, and the Silurian interval, with this immature oil gas generation window and 2 over mature oil and gas perspective for the area. So in conclusion, the evolution of fall and thrust belt required time data constraint in order to analyze the petroleum system components. This is important for this complex multivariable system in Bolivia, in particular to this geological cross-section we developed. We integrated the geological constraint and the thermochronological and geochronological data into this scenario to develop the structural interpretation. We developed a thermokinematic model in 4 steps, getting simulated cooling agent and time temperature paths successfully comparing the measured data. The different models performed permitted to conclude low geothermal gradients around 18 to 20 degrees per kilometer from 7 to nowadays million years. And finally, the numerical modeling allow us to evaluate the oil and gas perspective in the areas. Thanks to you all.